Star formation has been an ongoing process since the very early stages of our universe, usually from the results of dead remnants from previously existing stars. This carries on the cycle of stars for billions of years to come. Today, a lot of these remnants appear to us as beautiful, colourful regions that are all around us in the local universe. Hello everyone, and welcome back to the C-Squared channel. In my previous video, where I talked about brown dwarfs, I briefly covered how stars are normally formed within something called stellar nurseries. But for this video, I'm going to be talking more about these regions themselves. So to put it very simply, a stellar nursery is a region of extremely dense gas, primarily composed of hydrogen and helium, along with other trace amounts of other elements. So this particular region is under a ton of gravitational influence and pressure, which after quite a long period of time, we're going to say probably a few millions of years, stars will eventually begin to form from them. They also typically are located inside what is known as a nebula. So this is the remnants of a dead low to mid mass star. So pretty much these are stars that look around the same as our sun, around the same kind of size, mass, that kind of composition. And this happens when layers of stellar mass are ejected from the star's core as it dies. So you have the central star, as it approaches the end of its cycle, it kind of just lets out all the big layers of its mass, and then you eventually are left with what is known as a planetary nebula. So that is what eventually becomes a new place for new stars to form. So usually the first thing that comes to people's minds when hearing about, these kind of stellar nurseries could be the pillars of creation, and this has become one of the most famous photographs ever taken in outer space. So this is a region of very dense gas located within the Eagle Nebula, and this is located in the constellation of Serpens. This nebula consists of other similar star-forming regions, so it's not just the pillars of creation, but the nebula contains a whole load of other stuff. So we can see it here. We have the spire, we have several Bok Globules in some places, and that's something I'll be talking about later in this video. And there's even an open cluster of very young stars located right next to the pillars of creation. But how do we categorize these kind of star-forming regions? Because obviously there are a lot of them, and they all come in different varieties. They come in a huge variety of different shapes, sizes, and categories. So how do we categorize them, and what are the differences between them? So I'm going to quickly just discuss two of the more common types of stellar nurseries that are out there and are easily observable, easily studied. So the pillars of creation example that I just talked about belongs to the Eagle Nebula, and the Eagle Nebula belongs to a wider category of stellar nurseries that are called H2 regions. So these regions are made of gas and clouds. Again, like with every stellar nursery, they're all made up of that. But the composition of H2 regions is formed of ionized hydrogen. So this means that, unlike with a normal hydrogen atom that has one proton in the middle and then one electron orbiting around it, in the H2 case, which is what makes up these H2 regions, the electron is lost from the atom. So all you're left with is quite simply just a single proton. And so that is what the ionized hydrogen is. So this is, the H2 region, I should say, is the most common type of star-forming regions out there, I would say. And probably is the most common you would find as well when, observing nebulae, because in a sense they're all kind of H2 regions, really. So some of the examples we could take of these H2 regions, other than, the Eagle Nebula, we have the Eta Carinae Nebula, Horsehead Nebula, Tarantula Nebula, NGC 604, and the California Nebula. So all these regions have a few similarities. Two main ones though. For one, they're all nebulae. So this means that they have all emerged from dead stars that existed in these locations in the past. And as I've said, when a star dies, it ejects all the mass, and then the beautiful patterns that you can see in all these images, they're all just the results of the dead stars. These are all planetary nebula. So secondly, they all appear to be quite bright when you look at them through telescopes. So if you went to get your telescope, put it outside the window at night and look out, if you can, then you should see these bright little patches in the sky, which usually are nebulae, so they're generally very bright. The exception to this, in these set of images at least, is the California Nebula, but I'll talk about why. So the brightness for all the other nebulae, though, the brightness arises from newly born blue stars that emit a lot of radiation. So because the bright blue stars are usually the hottest and they're usually the most irradiative ones. They're ones that give out the most amount of radiation into the surroundings. And so what happens is that the radiation from these new stars inside the nebulae, they light up the region around them, because that's because radiation interacts with the hydrogen that make up the H2 regions, and this happens as the radiation escapes into the universe. So they need to get through the hydrogen atoms to actually get out into the universe, and to do that they are constantly interacting with them, and so they just light them up in a way. So the exception though, in these images at least, is the California Nebula. So in the case of this one, this nebula appears to be very dark and dim, and that is because hydrogen atoms are generally recombining with the lost electrons that are floating around in the H2 region. Remember, they are ionized. In some cases they're ionized, and in other cases, it's not just hydrogen atoms, but other atoms as well, and there would be collecting up lost electrons and, just to become stable. And in doing that, they release a lot of, they release radiation. But the radiation they emit usually gives off light that looks to be around in the red region. So that's why in this case you can see the California Nebula looks quite reddish here. Another thing is that the California Nebula can be considered as a dark nebula, so hence why it appears to be very dim. That's just literally the different kind of classification for the nebula. Okay, so there's a different kind of category then. We've talked about H2 regions, but there's another kind that's quite interesting. They are located within nebulae, and they are located within the H2 regions themselves. So you have the nebulae, and you have the H2 regions, like the general category, as one stellar nursery. And then within that, you have another stellar nursery of more confined regions, very small regions. So these appear to look as very small, dark, blob-like structures of opaque clouds. So these are areas where star formation has actually taken place already, and they are known as Bok Globules. So these are named after Bart Bok, who discovered them in the 1940s. So these bizarre regions usually form binary or multi-star systems. So this means that they produce two or more stars that tend to just orbit each other. Since these globules appear so dark to us, we can say that they are very absorbent, since they seem to take in a huge range of wavelengths of incoming radiation, and obviously nothing really gets emitted out from it, so they just appear completely dark. They just absorb everything. But while they are certainly not big in size, the radiation from the surroundings that gets absorbed actually doesn't make it very far inside at all, into the core of the globules at least. So they get absorbed usually in the surface regions, and then that's it. So because of this, almost no radiation gets inside, and so the core temperatures of these globules actually get extremely cold. And by extremely cold, I'm talking like down to at least 20 Kelvin. This corresponds to minus 253.15 degrees Celsius, or for the Americans, minus 423.67 degrees Fahrenheit. That is unimaginably cold. So, two of the more famous types of Bok Globules that are out there, the ones that, some examples I can give here, are Thackeray's globules and Barnard 68. So in the case of Thackeray's globules, these reside deep inside a nebula called IC2944, and they appear to be widely distributed across a portion of the nebula, and you can see it right there, it's usually in that little corner. But one remarkable feature is that the largest globule here, at least from our point of view, looks strikingly similar to Australia. So that's just a very odd thing that it's a very interesting coincidence that happened. So for the other globule, Barnard 68, this seems to be a single isolated globule that can be observed in the constellation of Ophiuchus. This one is only half a light year across, with a mass that is twice of the sun. So, it's generally small, but the mass is quite concentrated in that region. However, due to the way the globule looks in this image, you can see the structure looks quite well defined. You can see you can kind of make out the edges very well, and it looks to be kind of somewhat spherical. It's getting there. So this means that it is actually on the verge of gravitational collapse, where gravity will eventually overcome the outward pressures inside the globule. So this means that gravity will eventually just cause the cloud just to collapse in on itself, and this will form a new star. It is expected to probably happen in about 200,000 years. So for our lifetime, our scale, this is still extremely long, but for an astronomical scale, this is a very short amount of time. So you may have seen this image used in some places to describe something called the Boots void. So it is usually represented by this image for some reason, but in fact the Boots void is something entirely different to Barnard 68. What this image here is a globule, right? It's not the Boots void. So to clear some air about this confusion, the image of Barnard 68 here is far too small to resemble anything like a void, because you can clearly see here it looks like it's literally a cloud of dust and gas. So it is way too small to actually even look like a void. And to remind you, Barnard 68 is literally a cloud of very dense gas, and it's not an empty region of space, because that's what a void is. So there's definitely something in Barnard 68, but we just can't see any light coming from it. So that's why there's this confusion that Barnard 68 is used as a representation of Boots void, because it isn't. It's not Boots void at all. It's something entirely different. So, lastly, while this isn't quite related to star formation, it's worth talking about anyway, since this is a very fascinating aspect of some of the nebulae that we have out there, and it can be kind of linked to Bok Globules in a way. So let us consider the Helix Nebula, this very pretty looking image here. It's very cool, distinct rings of planetary nebula. It's a whole load of rings here. And it is located in the constellation Aquarius. So if you observe the regions within the outer ring, you can see these weird bubble-like structures forming all around it. They seem to look very similar to Bok Globules actually, but in fact these are known as cometary knots, and they are very prevalent in this nebula, not only in the Helix Nebula, but they appear in other nebulas as well. Some examples I could give right off my mind here is Eskimo Nebula and the Ring Nebula. Both of those also have these cometary knots, these kind of bubbles that form around the outer ring. So, a zoomed in photo of these knots shows that they exist as long strings of very dense gas and clouds. Again, this is very similar to a Bok Globule. But the reason why they are called cometary knots is because they have a central core point at the tip of the globule. So you can see there you got a very well-defined global region. And then there is a long trail of gas behind it. And another key thing to note is that all of these knots are pointing towards the center of the Helix Nebula in this case. But you can see this happens in the other nebulae I talked about as well. And so this can be very analogous to looking at it as comets orbiting the sun in our solar system, because they consist of a rocky core at the tip, and then there's this long trail of ice behind them. And as they orbit around the sun, the comets always face towards the sun. The trail's always looking away from the sun. So the resemblance of comets is why we use the name cometary knots to describe these nebulae. Now, unlike Bok Globules, they don't form stars. What they will form instead, eventually, given a long period of time, they will probably form a lot of moon-sized objects. So quite a lot of moons, asteroid-type objects, usually quite big. Usually, you would say anywhere between a range of, I don't know, Pluto to the moon, you could say. So, in conclusion, to end off this video, stellar nurseries form the foundation of new stars in our universe, starting from the remnants of old dead stars that came before them. These types of regions come in all shapes, sizes, and categories, but the ones I talked about here today are some of the more fascinating and beautiful aspects of what is really out there in the cosmos. So thank you guys so much for watching this video. Be sure to check out my secondary channel, C Cubed, if you want to look at general math stuff. It probably won't be very interesting to most people, but I'm doing stuff there. But yeah, so that's all for this video. Thank you guys for watching.